Hello. Welcome to the Spirit of Apollo. I'm your host, Mark Lesmeister. In this episode, we are going to examine what the Apollo astronauts, especially the Apollo 11 astronauts, did during their extravehicular activities, or EVAs, on the surface of the moon. But first, let's take a look at what Bag 3 adds to our Lunar Module model. So this is the completed descent stage of the model. The level of detail is quite remarkable, in my opinion. Shows the ladder over here that the astronauts use to exit and re-enter the LEM. This little platform over here is called the Mesa. We will talk more about that in a moment. You can see the reflective coating here that is used to protect the astronauts and the lander from micrometeorite strikes and thermal protection. On the back side here is another little compartment that we will talk about later. This is the SEQ bay. Whether we are old enough to have watched it live or we learned about it in our history classes, most of us are familiar with what happened in July of 1969 when Neil Armstrong and Buzz Aldrin became the first human beings to walk on the surface of the moon. I'd like to take a closer look at what they did during those extravehicular activities. And so to that end, I went ahead and completed the ascent stage of the model so we could use the entire model to talk about their activities. We'll talk about building the ascent stage in our next episode. About 6.5 hours after touchdown, the astronauts have both donned their EVA equipment and the hatch has been opened. Neil exits the LEM to the platform at the top of the ladder called the porch. The picture on the right, taken by Neil later, shows Buzz climbing down the ladder with the porch visible above him. At the top of the ladder, Neil pulls a cord that releases the modularized equipment stowage assembly, or MESA. The MESA is a shelf that can swing down to allow access to equipment the astronauts will need during their EVA. The TV camera that will broadcast Neil's first steps on the moon is mounted on the MESA. Buzz turns on the camera by closing the circuit breaker. He will also record the event using a 16mm film camera. Neil climbs down to the footpad at the base of the ladder, then tests the effort required to reach the lowest rung of the ladder. Then he climbs back down to the footpad.
I'm going to step off the LEM now. That's one small step for man, one giant leap for mankind.
One of Neil's first tasks on the lunar surface was to collect a contingency sample that he would store in a pocket of his EVA suit. This was to ensure that even if the astronauts had to leave the moon in a hurry, they would have at least one sample of the lunar soil. Now it was time for Buzz to come to the surface. As you can see from this shot of the checklist on his glove, one of his first tasks was to set up the solar wind collector, or SWC. This was a sheet of aluminum foil that was stored in the MESA. It was intended to capture ions of helium, neon, and argon that are present in the solar wind. Deploying the SWC at the beginning of their time on the surface would maximize the time the collector was exposed to the solar wind. The SWC was retrieved by the astronauts before leaving the moon. One of the most famous activities in their EVA wasn't on either astronaut's official checklist. The flagpole they planted had a horizontal support bar so that the flag would fly proudly even in the airless environment of the moon. I suspect that if we asked people what the astronauts did on the moon besides plant a flag, most people would mention moon rocks. And it is true that the missions did collect an enormous number of geological samples. The 6 missions that landed on the moon brought back a total of 2,196 samples with a total mass of 382 kilograms. One conclusion drawn from the analysis of these samples from the various missions is that the moon and Earth are similar in composition. This is one of the pieces of evidence supporting the idea that the moon is not a captured asteroid, as such an asteroid would likely be different in composition from the Earth. Instead, the similar composition favors the view that the moon was formed when the Earth was hit by a Mars-sized object, which scientists have named Theia, billions of years ago. In addition to collecting the samples, the Apollo astronauts took about 25,000 still photographs, as well as numerous film movies and live video feeds. Besides being a source of inspiration and wonder, these images provided important scientific data about the geology, or rather selenology, of the moon. Even the depth and sharp definition of the footprints give clues to the composition of the lunar soil. On Apollo 11, the astronauts would set up 2 long-term experiments as part of the early Apollo Scientific Experiments package. These experiments were stored in the Scientific Equipment Bay, SEQ, on the opposite side of the LEM from the MESA. The Laser Ranging Retroreflector, or LR cubed for short, was a device made up of retroreflecting cubes. These retroreflecting cubes reflect light back in the direction from where it came. By bouncing laser beams off of the reflectors from Earth and then detecting the reflections using telescopes, scientists can measure the position of the moon to a precision of a few millimeters. The passive seismic experiment package on Apollo 11 used 3 low-frequency seismometers to measure seismic movement along the horizontal and vertical axes, and a high-frequency seismometer that detected vertical motion. Much of what we know about the interior structure of the moon comes from studying seismic disturbances. The passive seismic experiment on Apollo 11 relied on solar power, which has a severe disadvantage for lunar surface experiments. Solar power doesn't work well during the long lunar nights, which last half a month. Later Apollo missions would deploy a more extensive set of experiments called the Apollo Lunar Surface Experiment Package, or ALSEP. Now, the ALSEP had, in addition to the experiments, a central station that provided communications and power for all the experiments. Solar panels were not required because the central station received its power from an RTG. Here to tell us about RTGs is a special guest, astronaut Mark Watney. Let me see if I can raise him. Mark, are you there? Okay, so Mark, we're talking about RTGs today, as used by NASA. What's an RTG?
The radioisotope thermoelectric generator.
Don't you have another name for RTGs?
The big box of plutonium, Mark.
Well, that doesn't sound very reassuring. Why does NASA use RTGs?
I get it. RTGs are good for spacecraft, but if they rupture around humans, no more humans.
Thanks, Mark. Of course, that was the fictional astronaut Mark Watney, played by Matt Damon in the movie The Martian. However, RTGs are a very real technology that NASA has used in situations requiring long-term electrical power where maintenance is impossible, including the Voyager missions and the Apollo science packages. In this picture from Apollo 16, the silvery device in the foreground is a passive seismic experiment. The block in the middle of the picture is the central station, and the black fin device behind the central station is the RTG. The RTGs and the LSEPs lasted until at least 1977, when monitoring the experiments was discontinued. Some of the samples returned by the Apollo astronauts were set aside for later analysis, under the assumption that methods of analysis would improve over the years, and that in fact did happen. There are still the retroreflectors on the surface of the moon, and they continue to be used to learn new things about the moon. So Project Apollo keeps giving us information. In the decades since Project Apollo, we have continued to explore the moon using robotic explorers and satellites. But ultimately, there is no substitute for human beings when it comes to exploration. That is why NASA, in conjunction with several other space agencies, has planned a series of missions with the goal of returning astronauts to the surface of the moon in the very near future. In fact, if all goes well, next month we will see a flyby of the moon for the first time since the 70s in the Artemis 2 mission. But we'll talk more about that in our next episode. Until then, Godspeed.